millions of kilometers from home. A spacecraft the size of a small car is drifting through absolute darkness when its instruments register something wrong. A wave of charged particles, moving at a meaningful fraction of the speed of light, has just slammed into its hull. For a machine built from silicon and copper, this is not a metaphorical storm. It is a physical bombardment, proton by proton, each one capable of flipping a single bit of memory, or in a worse case, burning out a transistor entirely. The question this raises is not dramatic for the sake of drama. It is one of the most practically important questions in modern space exploration, one that engineers, physicians, and mission planners alike return to with every new spacecraft launched. Can our silent voyagers actually survive the environment? We keep sending them into DOT to understand why this question matters right now. In the year 2026, it helps to know where the sun is in its cycle. The sun does not burn steadily. It breathes in a rhythm that repeats roughly every 11 years, swinging between quiet minimums and violent maximums. Solar cycle 25, the current cycle, reached its peak sometime around 2024 and 2025, and the elevated activity has continued into 2026, with researchers noting that this cycle has produced more intense and more frequent eruptions than several of the cycles that came before it. Sunspot counts, which serve as a rough proxy for magnetic turbulence on the solar surface, climbed higher than many forecasters expected. That surprise matters, because it means every mission currently operating beyond Earth's protective bubble is flying through conditions that are, in a very literal sense, more hostile than the models predicted when those missions were designed. The underlying cause of this 11-year rhythm lies deep within the sun itself, in a process called the solar dynamo. The sun is not a solid body, but a churning sphere of ionized gas, and different latitudes of its surface rotate at different speeds, a phenomenon called differential rotation, with the equator completing a rotation in roughly 25 days, while the polar regions take closer to 35 days. This uneven rotation gradually stretches and twists the sun's internal magnetic field lines, winding them tighter and tighter over time, somewhat like an elastic band being wound around an axle, until the resulting tension becomes concentrated enough to produce sunspots, dark, relatively cooler regions on the solar surface, marking areas of intense magnetic field strength. As a cycle progresses toward its maximum, this magnetic winding grows so pronounced that the sun's overall magnetic field eventually flips polarity entirely, north becoming south and south becoming north, before the whole process begins gradually unwinding and building toward the next cycle. This dynamo process, while broadly understood in outline, still contains genuine, open questions at the level of detailed prediction, which is part of why forecasting the precise strength of any future solar cycle, including whichever cycle follows the current one, remains an imprecise science, closer to a probabilistic weather forecast than an exact calculation history offers. A warning about what the sun is truly capable of. In 1859, a British astronomer named Richard Carrington was sketching sunspots through a telescope when he witnessed an intense white flash erupt from the solar surface, an event now remembered as the Carrington Event. Within about 17 hours, the resulting geomagnetic storm struck Earth, so powerful that telegraph operators around the world reported sparks leaping from their equipment. Some telegraph lines catching fire even after operators had disconnected their batteries. Apparently powered entirely by currents induced in the wires by the storm itself. Auroras were reported as far south as the Caribbean, bright enough in some locations that people reportedly read newspapers by their light in the middle of the night. At the time, the only real technology vulnerable to this kind of event was the telegraph network. Today, the same class of storm would strike a civilization built on satellites, GPS navigation, high-voltage power grids, and a fleet of robotic spacecraft with no telegraph-era tolerance for interrupted electricity. A storm of comparable intensity has not struck Earth directly since instruments capable of measuring it in detail existed, which is precisely why solar physicists study events like Carrington's so intently, treating it not as ancient trivia but as a genuine benchmark for worst-case planning. A less famous but arguably more chilling episode occurred in August of 1972. In the gap between the Apollo 16 and Apollo 17 missions, when no astronauts happened to be traveling between the Earth and the Moon, a massive and extremely fast-moving solar event erupted during that narrow window, producing a radiation storm that later analysis suggested could have delivered a dangerous, potentially life-threatening dose to an astronaut caught outside a spacecraft or lunar module during a moonwalk at the time, because the timing happened to fall between missions rather than during one. No crew was ever actually exposed, but the event has since been studied closely by radiation researchers precisely because it illustrates how much of survival in these earlier eras of exploration depended on fortunate timing as much as deliberate engineering. Later reconstructions of the event, using instruments that did exist at the time even though no crew was present to be exposed, estimated the radiation dose an unprotected astronaut on the lunar surface might have received, and the resulting figures were sobering enough that they have since been used as a specific benchmark case in modeling worst-case solar events for the far more radiation-exposed lunar surface. Missions currently being planned under the Artemis program. It is a sobering historical reminder that current mission planning treats forecasting and shielding not as optional refinements but as essential safeguards against a kind of event that has already, quietly, come close to causing tragedy once before. A smaller, but still highly instructive, preview came in October and November of 2003. During a period sometimes called the Halloween storms, a rapid sequence of powerful flares and coronal mass ejections erupted from the Sun over roughly 2 weeks, producing some of the most intense radiation storms ever measured by modern instruments. Astronauts aboard the International Space Station were directed to shelter in a more heavily shielded section of the station. Several Earth-orbiting satellites experienced instrument anomalies or temporary outages, and at least one satellite was lost entirely. Even a spacecraft that was not orbiting Earth at all felt the effects. The radiation detector aboard NASA's Mars Odyssey orbiter was saturated so severely by the incoming particle flux that the instrument was effectively blinded for a period afterward, a vivid demonstration that no distance from the Sun, at least within the inner solar system, is automatically a safe distance. Modern flare intensity is measured using a logarithmic scale that classifies events into letter categories. with C-class flares representing relatively minor events, M-class flares representing medium, occasionally disruptive events, and X-class flares representing the most powerful eruptions the Sun produces, each step up the letter scale representing roughly a tenfold increase in energy released. The Halloween storms included some of the strongest X-class events on record, and the fact that Solar Cycle 25 has already produced multiple significant X-class flares is part of why researchers have been watching this cycle so closely, taught to appreciate why this is dangerous at a physical level. You first have to understand what a solar flare actually is. A flare is a sudden, localized brightening on the sun's surface, caused when tangled magnetic field lines snap and reconnect, releasing energy that has built up over hours, days, or weeks. This process, called magnetic reconnection, converts stored magnetic energy into heat, light, and the acceleration of charged particles, sometimes within a matter of minutes. The most powerful of these events, classified as X-class flares, can release energy equivalent to billions of hydrogen bombs detonating simultaneously. Often, though not always, a flare is accompanied by a coronal mass ejection, a colossal bubble of magnetized plasma that erupts outward from the sun's corona at speeds that can exceed 1,000 kilometers per second. If a coronal mass ejection is aimed at a spacecraft or at Earth, the plasma cloud can take anywhere from under a day to several days to arrive, carrying with it a magnetic field that can slam into anything in its path. Understanding these eruptions well enough to predict them has required getting closer to the source than any spacecraft had ever dared. NASA's Parker Solar Probe, launched, was built specifically to fly through the sun's outer atmosphere, the corona, protected by a heat shield made of reinforced carbon composite roughly 11.5 centimeters thick, capable of withstanding temperatures exceeding 1,300 degrees Celsius on the sun-facing side, while the instruments just behind it operate at close to room temperature. This extraordinary design allowed the probe to fly closer to the sun than any human-made object in history, eventually passing within about 6 million kilometers of the solar surface. Data gathered during those passes helped resolve a long-standing puzzle: why the sun's outer corona is counterintuitively hundreds of times hotter than the visible surface beneath it. Evidence gathered by Parker's solar probe pointed toward rapid magnetic reversals in the solar wind, nicknamed switchback, as a significant contributor to heating and accelerating the stream of charged particles the sun constantly sheds into space. This matters directly to the question of spacecraft survival, because a better physical understanding of how and why the solar wind accelerates, and how flares and coronal mass ejections form within that same turbulent environment, feeds directly into improved forecasting models, the same models mission controllers rely on to decide when a distant probe should be commanded into safe mode before a storm ever arrives for Earth. The effects are often beautiful before they are dangerous. The same charged particles that threaten spacecraft also collide with atoms in our upper atmosphere, exciting them and producing the shimmering curtains of light we call auroras. But that beauty is really evidence of a planetary defense system at work. Earth's magnetic field, generated by the churning motion of molten iron in our planet's outer core, creates a protective magnetosphere that deflects the vast majority of incoming solar particles around the planet rather than through it. This magnetosphere extends far beyond the atmosphere itself, forming an invisible shield shaped almost like a windsock, compressed on the side facing the sun and stretched into a long tail on the side facing away. Anything operating on Earth's surface, and much of what orbits close to Earth, is protected by this shield. It is one of the underappreciated reasons life on this planet was able to develop and persist for billions of years without being sterilized by the sun's more violent moods, the same storms that threaten deep space probes do not spare Earth's own infrastructure either. Even with the magnetosphere's protection, when a coronal mass ejection compresses and disturbs Earth's magnetic field, it can induce electrical currents in any sufficiently long conductor, including high-voltage power transmission lines. These geomagnetically induced currents can overheat and, in rare severe cases, damage large transformers that form the backbone of regional power grids, a vulnerability demonstrated dramatically in March of 1989, when a geomagnetic storm caused a cascading power failure that left the Canadian province of Quebec without electricity for approximately 9 hours, affecting millions of people. Events like this are part of why agencies, including the United States Space Weather Prediction Center, now treat solar activity monitoring as a genuine public infrastructure concern, issuing regular forecasts and alerts in language deliberately similar to ordinary terrestrial weather reports, precisely because the practical stakes for power grids, aviation routes near the poles, and satellite operators alike are not limited to spacecraft hundreds of millions of kilometers away. Understanding deep space survival, in other words, is really a specific and particularly extreme application of a much broader field now generally known as space weather science. Within that magnetosphere lie to donut-shaped regions called the Van Allen radiation belts, discovered in 1958 by instruments aboard Explorer 1, the first satellite launched by the United States. These belts consist of charged particles, mostly electrons and protons, trapped by Earth's magnetic field lines, spiraling back and forth between the northern and southern hemispheres like beads threaded on an invisible wire. The inner belt, populated largely by high-energy protons, and the outer belt, populated largely by electrons, whose density and energy can swell dramatically during geomagnetic storms, together form a hazardous region that engineers must account for when designing any satellite whose orbit passes through them. Far from being a fixed, static structure, the Van Allen belts are known to swell, shrink, and occasionally split into additional temporary belts in direct response to solar activity. A discovery made possible by NASA's Twin Van Allen Probes mission, which operated from 2012 to 2019 and revealed a level of dynamic complexity in this region that had not been previously appreciated. Satellites in medium Earth orbit, including the constellations that provide global navigation signals, spend significant portions of their working lives inside these belts, which is one of the many reasons even Earth-orbiting technology, not just deep space probes, must be engineered with genuine radiation tolerance in mind. Earth is far from unique in generating this kind of protective structure. Though the scale varies enormously across the solar system, Jupiter's magnetic field is the strongest of any planet in the solar system, generated by a deep interior layer of metallic hydrogen, behaving as an electrical conductor under the planet's crushing internal pressure. And it produces a magnetosphere so vast, if it were visible to the naked eye from Earth, it would appear larger in the sky than the full moon, despite Jupiter's enormous distance. This same powerful field is precisely why the radiation environment around Jupiter is so much more dangerous than Earth's own belts, since a stronger magnetic field traps and accelerates far more charged particles into a correspondingly more intense radiation belt system. The very environment Juno and Europa Clipper have had to be so carefully engineered to survive. Saturn, too, generates a substantial magnetic field and its own auroras. Observed in ultraviolet light by NASA's Cassini spacecraft during its 13 years orbiting the planet, though Saturn's field is considerably weaker than Jupiter's and shaped in an unusually symmetrical way that has itself puzzled researchers studying planetary dynamo theory. Comparing these different planetary magnetic fields, weak, strong, symmetrical, or entirely absent, as in the case of modern Mars, gives scientists a broader natural laboratory for testing theories of how planetary interiors generate magnetic fields in the first place. Insights that feed back into a more complete understanding of Earth's own magnetosphere and, by extension, the radiation environment every spacecraft leaving Earth must eventually contend with beyond the moon, though that protection effectively disappears once a spacecraft crosses what is sometimes informally called the lunar gateway, the last meaningful boundary of Earth's magnetic influence. It is on its own. There is no shield, no atmosphere to absorb incoming radiation, nothing standing between a fragile electronic system and the raw output of the sun. This is the moment where deep space missions stop being protected by planetary physics and start depending entirely on human engineering. Mars presents a particularly instructive comparison here, because unlike Earth, it lacks a strong global magnetic field of its own today. Evidence gathered by NASA's MAVEN orbiter, which arrived at Mars in 2014 specifically to study the planet's upper atmosphere, indicates that Mars once likely possessed a magnetic field roughly comparable to Earth's, generated by a similar molten core dynamo, but that this field shut down billions of years ago as the planet's interior cooled and its core dynamo stalled. Without a sustained magnetosphere to deflect the solar wind, Mars has spent billions of years having its thin atmosphere gradually stripped away by direct exposure to the sun's particle stream, a process MAVEN was able to measure directly, observing atmospheric particles being carried away into space in real time. The practical consequence for any future human mission is significant. Astronauts standing on the Martian surface would have only a thin atmosphere and no meaningful planetary magnetic shield standing between them and incoming radiation, meaning surface habitats, much like the spacecraft that carried the crew there, would need their own dedicated shielding strategy rather than being able to rely on the destination planet itself for protection. Unlike explorers who have only ever operated within the relative safety of Earth's own magnetosphere, that engineering begins at the level of individual atoms. Modern spacecraft processors are built from silicon, arranged into transistors so small that some modern designs packed features measured in mere nanometers, a scale where a single high-energy particle can do outsized damage. When a high-energy proton strikes silicon, it can dislodge electrons, creating a cascade of charge that a processor's circuitry may misinterpret as a legitimate electronic signal. This is called a single event upset, and in the best case, it flips a single bit of data from a 0 to a 1, an error that mission engineers can often catch and correct. In a worse case, the particle can trigger what is called a single event, where a parasitic circuit path opens up and allows current to flow uncontrolled, generating heat that can permanently damage the chip if power is not cut in time. In the worst case, a particularly energetic strike can physically destroy a transistor. This is why the phrase rad-hardened, short for radiation, appears constantly in discussions of deep space hardware. Radiation hardening is not a single technology, but a whole philosophy of design. Layered defense against an enemy that cannot be seen and cannot be reasoned with. One major technique is called silicon insulator design, where a thin layer of insulating material is placed beneath the active silicon layer, reducing the volume of material in which a stray particle can generate a damaging charge cascade. Another is the deliberate use of larger transistor geometries in critical systems, sacrificing some processing speed and efficiency in exchange for the fact that a single particle strike affects a smaller percentage of a larger, more robust structure. Engineers also build in redundancy at almost every level. Triple modular redundancy, for example, runs the same calculation through 3 separate identical circuits simultaneously and then compares the results. So, if a stray particle corrupts one output, the other 2 can outvote the error, and the system can flag the fault and move on without ever presenting a wrong answer to the rest of the spacecraft. Memory systems receive their own dedicated layer of protection through error-correcting code, a mathematical scheme that stores small amounts of extra redundant data alongside the primary information, allowing onboard software to detect when a stored value has been altered by a stray particle strike. In many cases, to reconstruct the original correct value automatically, without ever needing to interrupt the spacecraft's normal operation or alert engineers on the ground unless the correction rate itself becomes unusually high, which would itself serve as an early warning sign of worsening radiation. Conditions worth monitoring closely. None of these design choices are simply assumed to work before a single component is approved for a mission. It is typically taken to a particle accelerator facility here on Earth and deliberately bombarded with protons, heavy ions, or neutrons at controlled energies, allowing engineers to measure exactly how many single event upsets or latch-ups occur at a given radiation dose, long before the part is ever integrated into a spacecraft. This process, sometimes taking months for a single complex chip, produces a detailed statistical profile of how a component is expected to behave across the entire radiation environment a mission is likely to encounter. From the relatively gentle conditions near Earth to the considerably harsher belts surrounding a planet like Jupiter, engineers also rely heavily on what is sometimes called flight heritage components, an entire subsystem, designs that have already flown successfully on previous missions. A processor or memory chip with a strong flight heritage carries, a kind of trust that no amount of laboratory testing alone can fully replicate, because it has already proven itself against the genuine, unpredictable conditions of space rather than only a simulated approximation of them in a laboratory. This is part of why so many missions across different agencies and different decades have ended up relying on surprisingly similar families of radiation-hardened processors, reused and incrementally improved, mission after mission rather than reinvented from scratch. Each time, some of the most important facilities for this kind of testing are found not in a spaceport but at nuclear and particle physics laboratories originally built for entirely different scientific purposes. NASA's Space Radiation Laboratory, located at Brookhaven National Laboratory in the United States, uses a particle accelerator originally developed for nuclear and high-energy physics research to generate beams of protons and heavy ions matched to the energies and compositions found in galactic cosmic rays and solar particle events, allowing researchers to expose both electronic components and, in dedicated biological studies, cell cultures and laboratory animals to a scientifically accurate simulation of the deep space radiation environment without ever leaving Earth. This kind of shared infrastructure, originally built for particle physics but repurposed for space radiation research, illustrates how progress in understanding deep space survival often depends on scientific fields that, on the surface, seem entirely unrelated to space. Another example of how the challenge of surviving beyond Earth pulls together expertise from nuclear physics, materials, science, biology, and mission engineering into a single, cooperative research effort. If you have ever wondered why a deep space probe uses a processor that would have felt outdated in a home computer decades earlier, this is the reason. It is not a failure of imagination or a shortage of ambition. It is a deliberate trade-off, because a radiation-tolerant chip that runs slower is far more valuable, 100 million kilometers from the nearest repair technician, than a faster chip that might silently corrupt its own memory during the worst days of a solar storm. One specific family of processors illustrates flight heritage in action particularly well. A radiation-hardened processor originally developed in the 1990s, built around the same basic architecture as an early consumer workstation chip but re-engineered for radiation tolerance, has since flown aboard numerous missions, including the Curiosity and Perseverance rovers currently operating on Mars, precisely because its behavior under radiation exposure had already been so extensively characterized through earlier missions that engineers could plan around its known limitations with a high degree of confidence, even though far faster commercial processors had long since become available on Earth. More recently, a newer generation of radiation-hardened multi-core processors has begun entering service, offering substantially more computing power while still incorporating the same fundamental hardening philosophies, reflecting how this field advances incrementally, favoring proven reliability over the fastest available performance. Alongside this traditional approach, a newer philosophy associated with the rapidly growing commercial spaceflight sector has also emerged, sometimes summarized as favoring redundancy over exotic hardening, rather than paying the enormous cost premium for individually radiation-hardened components. Some commercial satellite constellations instead use relatively ordinary, commercially available electronics, but deploy them across large numbers of satellites, accepting that individual units will periodically suffer radiation-related glitches or even total failures, while relying on the sheer size of the constellation and inexpensive, rapid replacement launches to maintain overall service continuity. Both philosophies represent valid, scientifically grounded responses to the same underlying physical threat, simply optimized for different mission profiles. One favoring the irreplaceable, singular value of a deep space science mission, and the other favoring the replaceable, numerous nature of a large satellite constellation in Earth orbit. That trade-off extends beyond electronics and into the physical shape of the spacecraft itself. Every additional layer of shielding, usually built from dense materials like aluminum, tantalum, or in some cases, layered polyethylene, designed to slow down neutrons, adds mass. Mass is the currency of spaceflight. Every extra kilogram of shielding is a kilogram of fuel not carried, a kilogram of scientific instrument not launched, a kilogram that must be paid for with a more powerful and more expensive rocket. Mission designers are therefore forced into an unforgiving balancing act. Shield the most critical components heavily, accept calculated risk on less essential systems, and hope that statistical models of solar activity during the mission's expected lifetime were reasonably accurate. When a solar cycle turns out to be more violent than predicted, as Cycle 25 has in various respects, that calculated risk becomes a live gamble being played out in real time, hundreds of millions of kilometers from Earth. Few missions illustrate this trade-off more vividly than those sent to Jupiter, whose enormous magnetic field traps radiation belts far more intense than Earth's own, intense enough that a human standing unprotected near the planet's inner moons would receive a lethal dose of radiation within a remarkably short period. NASA's Juno spacecraft, which arrived at Jupiter in 2016, addressed this problem with a solution that looked almost medieval in its simplicity: a titanium vault with walls roughly 1 centimeter thick, built specifically to enclose the spacecraft's most sensitive electronics inside a dense metal box, reducing the radiation dose reaching the internal components by a substantial factor compared to leaving them unshielded. Even with the vault, Juno's instruments were expected to degrade steadily over the course of the mission, and engineers designed the mission timeline with that degradation explicitly built into their planning rather than treated as an unexpected failure. Europa Clipper, launched in 2024 to study Jupiter's icy moon Europa, faces an even more punishing version of this same environment during its repeated, close flybys of the radiation-soaked region near the moon, and its designers used a similar vaulted enclosure, combined with a flight plan that limits the total accumulated dose by carefully timing each flyby rather than lingering in the most dangerous regions any longer than scientifically necessary. Both missions demonstrate the same underlying principle. Since radiation cannot be eliminated, mission design becomes an exercise in managing exposure, spending a finite radiation budget as carefully as a mission spends its finite fuel. The choice of shielding material itself involves its own scientific trade-offs, not just a simple question of thickness. Dense metals like aluminum, historically the most common shielding material in spacecraft hulls, are effective against many types of radiation but can, as discussed elsewhere, generate a shower of secondary neutrons when struck by very high energy particles. Since the same dense atomic nuclei that block incoming radiation can also fragment under sufficiently energetic impacts, materials rich in hydrogen, including water, polyethylene plastic, and certain specially formulated composite materials, are generally considered more efficient at slowing down and absorbing high-energy particles per unit of mass. Because hydrogen nuclei are close in mass to the incoming particles themselves, making collisions more effective at transferring and dissipating energy, roughly analogous to the way a billiard ball transfers more of its energy in a collision with a similarly sized ball than with something far heavier or lighter. This is precisely why proposals for Mars transit shielding increasingly favor consumable supplies like water and food storage, and specially designed polyethylene layers arranged strategically around crew quarters, rather than simply adding more traditional metal shielding, since the same protective benefit can often be achieved using materials the mission needs to carry regardless, rather than dedicated shielding mass that serves no other function aboard the spacecraft. Engineers have also built in a last line of defense, a kind of digital hibernation called safe mode. When onboard sensors detect conditions consistent with an incoming radiation storm, or when something has already gone wrong and the cause is not immediately clear, a spacecraft's software can automatically shut down all non-essential systems, orient itself using only its most basic and most rigorously tested instructions, and essentially go quiet. Instruments power down. Data collection halts. The spacecraft focuses entirely on preserving its core memory, its attitude control, and its ability to communicate a heartbeat signal back to Earth. A machine curling into a protective posture and waiting for the storm to pass. Mission controllers have used exactly this kind of protocol on multiple missions when solar activity threatened onboard systems, deliberately silencing the vast majority of a spacecraft's functions to protect the small fraction that truly cannot be replaced. These are not hypothetical scenarios drawn up purely for planning documents. Voyager 2, decades into its mission, unexpectedly entered safe mode in early 2020, after an onboard error caused the spacecraft to fail to execute a scheduled maneuver, drawing more power than its aging systems could comfortably supply and triggering an automatic protective shutdown of its science instruments while engineers on the ground worked out how to safely restore normal operations across a radio round-trip delay of many hours in each direction. New Horizons, famous for its flyby of Pluto in 2015, has also experienced its own autonomous safe mode entries earlier in its mission, in at least one case triggered by a software timing issue rather than radiation directly, but resolved using exactly the same underlying philosophy. When in doubt, protect the core, shut down everything else, and wait for careful instructions from home. Juno, orbiting deep within Jupiter's radiation belts, has likewise entered safe mode multiple times over the course of its mission, occasionally attributed to the punishing radiation environment interfering with onboard systems despite the protection of its titanium vault. Each of these events, while alarming to read about in a news headline, actually represents the safe mode protocol succeeding exactly as intended, sacrificing days or weeks of active science operations in exchange for preserving a spacecraft that would otherwise have no way to recover from a more serious fault. Even when a spacecraft survives a solar event intact, the sun's violence does not stop at the hull. It reaches all the way back to Earth through the fragile thread of a radio signal. Deep space communication depends on incredibly faint transmissions, often measured in a fraction of a billionth of a watt by the time they reach a receiving dish on Earth. Having spread out and weakened across a journey of hundreds of millions or even billions of kilometers. A signal that faint is easily overwhelmed by interference, and the sun, during active periods, becomes an enormous and unpredictable source of radio noise across a huge range of frequencies. Solar radio bursts, generated by the same magnetic processes that produce flares and coronal mass ejections, can wash out the delicate signal from a distant probe the way a shout can drown out a whisper. This problem becomes particularly acute during a phenomenon called solar conjunction, when a planet, its orbiting spacecraft, and Earth line up with the sun directly between the transmitter and the receiver. During these windows, which occur periodically as planets follow their orbits, the sun's own radio emissions and coronal plasma sit directly in the communication path, sometimes for days or weeks depending on the mission and the alignment. Engineers refer to the most severe of these as blackout windows, periods where the interference becomes so overwhelming that reliable two-way communication with a spacecraft becomes effectively impossible. During these periods, most missions are pre-programmed to enter a conservative operational mode, essentially waiting out the interference before resuming full data transmission once the geometry improves. Mars missions provide the clearest recurring example of this challenge, since Mars and Earth pass through solar conjunction roughly once every 2 years as their orbits carry them to opposite sides of the Sun. During these periods, mission teams operating rovers, landers, and orbiters at Mars deliberately suspend sending new commands for a window lasting roughly 2 weeks, instead preloading each spacecraft with a conservative, thoroughly tested set of instructions to follow independently. Since a command corrupted by solar interference during this period could otherwise cause a rover to attempt a maneuver based on a garbled instruction, with no realistic way for ground controllers to intervene quickly if something went wrong, engineers have grown so comfortable with this recurring blackout that it is now treated as a routine, scheduled feature of Mars mission planning rather than an emergency, built into mission calendars years in advance. A good illustration of how what once might have seemed like an alarming vulnerability has been converted, through experience and careful planning, into a manageable and even mundane part of operating in deep space. To fight back against this fragility, ground infrastructure has had to keep pace. The Deep Space Network, a system of enormous dish antennas positioned roughly 1/3 of the way around the world from each other in California, Spain, and Australia, forms humanity's primary listening post for messages from beyond Earth. The spacing is deliberate as Earth rotates. At least one of these stations is always facing whatever direction a distant spacecraft happens to be, ensuring continuous coverage. Throughout 2026, engineers have continued upgrading these facilities, refining signal processing techniques and receiver electronics specifically to filter solar interference out of the data stream, using increasingly sophisticated software to distinguish the genuine, structured signal of a spacecraft from the essentially random noise generated by the sun's turbulent atmosphere. These upgrades matter enormously because a mission's scientific value is worthless if its discoveries cannot make the trip home through a curtain of solar static. The physical scale of this network is easy to underestimate. Each deep space network complex, located near Goldstone in California, Madrid in Spain, and Canberra in Australia, includes at least one enormous dish measuring 70 meters across, along with several smaller 34-meter dishes, all steerable with extraordinary precision, to track a target that may be moving across the sky at a rate that would be imperceptible to a casual observer, but must be tracked continuously to maintain a lock on a signal fainter than almost anything else engineered by humans. To increase sensitivity further, engineers sometimes use a technique called arraying, electronically combining the signals received by multiple dishes at the same complex, or even at different complexes, so that they reinforce one another, the way multiple listeners, straining to hear a whisper, can, together, catch words that any one of them alone might miss. Communication with the most distant operating spacecraft increasingly relies on a higher frequency radio band called co-band, rather than the older X-band historically used for deep space communication, because the higher frequency allows more data to be squeezed through the same faint signal, provided the receiving equipment and the weather at each ground station cooperate. None of this infrastructure was inevitable. It represents a continuously upgraded, multi-decade engineering investment, because the moment humanity stopped building bigger, more sensitive, more cleverly designed antennas, an entire category of missions already in flight would effectively go deaf, regardless of how well their onboard systems were performing. All of this discussion, so far, has concerned machines. But the same physics that threatens silicon chips threatens something far more precious, the human body. As space agencies plan increasingly ambitious crewed missions, including extended stays on the lunar surface and eventual journeys to Mars, the conversation shifts from protecting circuits to protecting cells. If you find this kind of deep, evidence-based science storytelling interesting, take a moment to follow along, because understanding how fragile our foothold beyond Earth really is only gets more important as these missions move forward. Radiation in deep space comes in two broad categories, and they behave very differently. The first is the sudden, intense burst associated with solar particle events, the same eruptions that threaten spacecraft electronics. These events are relatively rare and, importantly, somewhat predictable in the sense that they can sometimes be forecast hours in advance, giving astronauts time to retreat to a shielded area of a spacecraft or habitat. The second category is far more insidious: galactic cosmic rays, a constant, low-level rain of extremely high-energy particles originating from outside our solar system, likely accelerated by the shock waves of ancient supernova and other violent astrophysical events. Unlike solar particles, galactic cosmic rays are present essentially all the time, and they are made up of heavier, more energetic particles that are notoriously difficult to shield against using conventional materials. The leading explanation for how these particles reach such extraordinary energies involves a process called diffusive shock acceleration, in which charged particles are trapped near the expanding shock wave of a supernova, remnant and repeatedly bounced back and forth across the shock front by the surrounding turbulent magnetic fields, gaining a small additional boost of energy with each crossing until, after many such crossings over hundreds or thousands of years, some particles emerge with energies far beyond anything achievable in even the largest particle accelerators built on Earth. This mechanism, first proposed in a more general form by the physicist Enrico Fermi in the middle of the 20th century, remains the strongest supported explanation currently available, though the precise details of exactly which astrophysical sources contribute which fraction of the cosmic ray population reaching our solar system remain an active area of research, studied using instruments ranging from ground-based cosmic ray observatories to detectors carried aboard the International Space Station. A particularly concerning subset of galactic cosmic rays, often referred to by researchers using the shorthand HZE, meaning high atomic number and high energy, includes heavier atomic nuclei such as iron, stripped of their surrounding electrons and traveling at tremendous speed. Even though these heavier nuclei make up a relatively small fraction of the total cosmic ray population compared to lighter particles like protons, their greater mass and charge mean each individual particle deposits a disproportionately large and densely concentrated amount of energy along its track through tissue, producing a distinctive pattern of biological damage that researchers have studied, using both ground-based particle accelerator facilities designed to simulate space radiation and, more directly, through the health records of astronauts who have flown long-duration missions. When either type of radiation strikes the hull of a spacecraft, the interaction does not simply stop at the metal skin. High-energy particles collide with atomic nuclei in the shielding material itself, and these collisions can produce a spray of secondary particles, including neutrons and lighter fragments, that continue onward into the spacecraft's interior. In some cases, thick shielding can paradoxically make secondary radiation worse rather than better, because the incoming particle fragments into a wider shower of secondary particles upon impact, a phenomenon engineers must carefully model when choosing shielding materials and thicknesses. This secondary radiation, striking human tissue, can damage the structure of DNA within living cells, sometimes breaking both strands of the double helix in a way that is particularly difficult for cellular repair mechanisms to fix correctly. Over time, this kind of damage is associated with increased cancer risk, and researchers have also raised concerns based on both ground-based experiments and studies of astronauts who have spent extended periods in orbit, that this radiation may have effects on the central nervous system, potentially influencing cognition and the connections between neurons. One of the most detailed pictures of how the human body actually responds to extended radiation exposure comes from NASA's twin study, conducted when astronaut Scott Kelly spent nearly a year aboard the International Space Station, while his identical twin brother, former astronaut Mark Kelly, remained on Earth. allowing researchers an unusually controlled genetic comparison. Blood and tissue samples collected before, during, and after the mission revealed measurable changes in gene expression, alterations in the length of protective caps on the ends of chromosomes called telomeres, and shifts in markers associated with inflammation and DNA damage repair, some of which returned toward pre-flight levels after Kelly's return to Earth, and some of which persisted for a longer period afterward. While a single pair of twins cannot establish broad statistical conclusions on its own, the study provided an unusually rich, individually detailed dataset that researchers have used to refine hypotheses about which biological systems appear most sensitive to the combined stresses of spaceflight, including radiation exposure, and which effects appear to be temporary versus potentially long, directly informing the design of the more cautious exposure limits and monitoring protocols used for subsequent long-duration missions. Current medical countermeasures remain, honestly, incomplete. Antioxidant compounds have been studied for their potential to reduce cellular damage from radiation exposure, and career radiation exposure limits are used by space agencies. To cap the total dose an individual astronaut is permitted to accumulate over a lifetime of missions. Shielded sleeping quarters, sometimes reinforced with water storage or other hydrogen-rich materials that are relatively effective at slowing down energetic particles, offer astronauts a safer place to retreat during a solar event. But a multi-year transit to Mars, of the kind mission planners have discussed, would expose a crew to months of continuous galactic cosmic ray bombardment, with no possibility of returning to Earth's protective magnetosphere partway through. Whether existing countermeasures are genuinely sufficient to keep an astronaut's body, and specifically their nervous system, intact and healthy across such a journey remains an open and actively researched question, not a solved problem with a simple, confident answer. Much of the concern about cognitive effects stems from controlled studies conducted on rodents, exposed to simulated space radiation at ground-based accelerator facilities designed specifically to reproduce the energy and composition of galactic cosmic rays. Several such studies have reported measurable changes in the structure of neurons and in performance on learning and memory tasks following exposure to doses roughly comparable to what an astronaut might accumulate during a multi-year Mars mission. Though translating results from rodent studies directly into predictions about human cognition carries real scientific uncertainty. Since human brains differ from rodent brains in scale, structure, and repair capacity in ways that are not yet fully understood, some researchers have also explored more speculative countermeasure concepts, including torpor or induced hypothermic states that would allow a crew to spend much of a long transit in a metabolically slowed condition. An idea borrowed partly from observations of natural hibernation in some animal species, on the theory that a slower metabolism might also reduce the rate of accumulating radiation-related cellular damage, alongside the more straightforward benefit of reducing the food, water, and habitat volume a mission would need to carry. It is important to be clear that induced human hibernation for spaceflight remains a genuinely early-stage research concept, studied primarily through small-scale physiological experiments rather than anything close to a proven, mission-ready technology. and no space agency currently plans to rely on it for a near-term Mars mission. Some of the clearest real-world data on this problem has come not from a crewed mission at all, but from an instrument riding along on a robotic one. The Radiation Assessment Detector, an instrument aboard NASA's Curiosity rover, began measuring radiation levels during the spacecraft's roughly 8-month cruise to Mars in 2011 and 2012, long before the rover ever touched Martian soil. Data from that cruise phase indicated that an astronaut making a similar round-trip journey to Mars using comparable shielding could accumulate a radiation dose considered close to, or in some mission profiles, potentially exceeding currently accepted career exposure limits from the transit alone, without even accounting for additional time spent on the Martian surface itself, where a thin atmosphere provides only partial protection. Compared to Earth, NASA has historically set career radiation exposure limits designed to keep an astronaut's added lifetime cancer risk below a defined threshold, with the specific numerical limits varying somewhat based on an astronaut's age and sex at the time of their mission, reflecting differences in biological sensitivity documented across large population studies. These limits were established with low Earth orbit missions primarily in mind, and adapting them responsibly to a multi-year Mars transit remains an active area of policy and scientific discussion, rather than a settled matter. Spacecraft designers have responded with several concrete engineering proposals, even if none has yet been proven across the length of an actual Mars mission. NASA's Orion capsule, intended to carry astronauts on missions around the Moon and eventually contribute to Mars mission architecture, includes a designed storm shelter concept in which crew members would use stowed equipment, supplies, and even water containers arranged around a central area of the capsule to create a temporarily reinforced shielded pocket during a significant solar particle event, a strategy sometimes referred to informally as a water wall, since water molecules rich in hydrogen are particularly effective at slowing incoming energetic particles per unit of mass compared to denser metals. This approach elegantly reuses supplies the crew needs anyway, rather than requiring dedicated shielding mass that serves no other purpose. The Artemis program's Lunar Gateway Station, planned to orbit the Moon and support future deep space missions, likewise carries dedicated radiation monitoring instruments, allowing researchers to gather continuous data on the radiation environment in cislunar space, well beyond Earth's main protective belts, but still relatively close to home, generating exactly the kind of long-duration dataset that will be needed before any agency commits astronauts to a multi-year Mars transit with full confidence in the shielding strategy chosen. Beyond the spacecraft itself, planners working on future lunar surface habitats as part of the Artemis program have looked to a resource that requires no launch mass at all: the Moon's own soil. Lunar regolith, the loose, fragmented material covering the Moon's surface, is being studied as a potential shielding material for future surface habitats, since piling even a modest depth of this material over or around a habitat module could substantially reduce the radiation dose reaching astronauts inside, using a resource already present at the destination rather than one that must be carried the entire distance from Earth at enormous cost. Engineers have proposed various construction approaches, including robotically excavating and piling loose regolith directly onto habitat structures, or processing it into denser building materials using techniques still being refined and tested. This general strategy, sometimes summarized by planners as living off the land, reflects a broader shift in thinking about deep space survival. Rather than trying to carry every gram of protection from Earth, future missions increasingly look for ways to harvest protection from the environment being explored, turning what is otherwise simply hostile, airless terrain into a resource that reduces the burden every subsequent mission must otherwise ship at great expense. Across the vacuum, this uncertainty is precisely why current human missions remain confined to low Earth orbit. More recently, the region around the Moon, where a return to Earth, or at least partial shelter, is realistically achievable within days rather than years. It is also why so much research effort across multiple space agencies and private companies is currently devoted to better radiation shielding materials, revised habitat designs, and a deeper understanding of the biological mechanisms involved. Because the physics of the problem will not change, and the only path forward is genuinely better engineering and genuinely better medicine. Meanwhile, out beyond even the reach of current human ambition, humanity's oldest interstellar envoys are quietly running out of time, not because of any single dramatic event, but because of the simple, patient arithmetic of decay. Voyager 1 and Voyager 2, launched in 1977, are powered not by solar panels, which would be useless at their current distance from the Sun, but by radioisotope thermoelectric generators, devices whose basic design traces back to earlier NASA missions and 2 decades of nuclear engineering research conducted well before either spacecraft ever left the launch pad. These devices convert the heat produced by the natural radioactive decay of plutonium-238 into electricity, using no moving parts and requiring no sunlight whatsoever. The catch is that plutonium-238 decays on a fixed schedule, with a half-life of roughly 87.7 years, meaning the heat output, and therefore the electrical power available to the spacecraft, has been steadily and predictably declining since the moment each generator was fueled. Decades before launch, the boundary the Voyagers crossed is not a simple, sharp line so much as a complex, layered structure that scientists have had to piece together gradually, using both direct spacecraft measurements and remote sensing from missions that never left the vicinity of Earth at all. NASA's Interstellar Boundary Explorer, a relatively small and inexpensive spacecraft launched in 2008, mapped this boundary region from a distance by detecting energetic neutral atoms, particles created when fast-moving ions from the solar wind collide with slower-moving neutral atoms drifting in from interstellar space, swapping an electron in a way that lets the resulting particle travel in a straight line back toward Earth, unaffected by magnetic fields, carrying information about the distant boundary encoded in its speed and direction. This remote mapping revealed a surprisingly narrow, ribbon-like structure of enhanced particle emission wrapping part-way around the heliosphere, a discovery that was not predicted by pre-existing models and that researchers are still working to fully explain. The Voyagers, meanwhile, provided the ground truth complement to this remote view, actually passing through the boundary and measuring the local plasma density, magnetic field strength, and particle population directly. Data that in some respects confirmed and in other respects complicated the picture built from Earth-based observations. Together, these two very different kinds of missions, one venturing physically outward and one observing patiently from near home, illustrate how understanding even the basic shape of our own solar system's outer boundary has required combining direct exploration with remote, indirect detection, since no single method alone could have produced a complete picture. Mission engineers have responded to this slow decline with remarkable ingenuity, systematically powering down individual instruments and heaters as available electricity has dwindled, prioritizing whichever systems still provide the most valuable scientific data or are most essential to keeping the spacecraft operational at all. Both Voyager probes have now traveled far beyond the boundary where the sun's outward stream of charged particles, called the solar wind, is finally overwhelmed by the pressure of the interstellar medium, the thin soup of gas and dust that fills the space between stars. Crossing this boundary meant the Voyagers became the first human-made objects to sample interstellar space directly, a genuine milestone in the history of exploration. But even this achievement has an expiration date. Engineers generally expect that within the next several years, the declining power output will finally fall below the threshold needed to operate even a single scientific instrument, and eventually below the threshold needed to keep the spacecraft's transmitter powered on at all. When that day arrives, communication with the Voyagers will end not because of a solar storm, a technical failure, or a catastrophic collision, but simply because the physics of radioactive decay reached its inevitable, quietly foreseeable conclusion. To put the scale of this decline in perspective, each Voyager's generator produced a little over 400 watts of electrical power at launch in 1977, comparable to a handful of household light bulbs, and that output has been declining by roughly 4 watts per year ever since. A slow and steady erosion rather than a sudden cliff. Engineers have already permanently switched off Voyager's cameras, its ultraviolet spectrometer, and several other instruments over the decades specifically to keep the remaining instruments, including detectors that study the interstellar magnetic field and plasma environment, running for as long as mathematically possible in 2023 and 2024. Mission engineers even took the unusual step of tapping into a small reserve of power, originally set aside as a safety backup for onboard heaters, judging that the scientific value of continued operation outweighed the risk of running certain components colder than originally intended, a decision that reflects just how carefully every remaining watt is now being negotiated. New Horizons, which flew past Pluto in 2015 and continues onward into the Kuiper Belt, uses a similar radioisotope generator design and faces a comparable long-term power decline, though because it launched nearly 3 decades after the Voyagers, it currently has considerably more operational life remaining, illustrating how the same fundamental physics of radioactive decay applies to every mission of this type, just started from a different point on the same steadily descending curve. Mission planners already treat this decline as a known, schedulable event rather than a surprise. penciling in rough estimates for when each remaining instrument will finally lose enough power to switch off for good, turning what could be read as a countdown to silence into instead a carefully managed, scientifically productive final chapter. This raises a broader and more uncomfortable question about the entire fleet of instruments and probes we have sent outward. Every spacecraft carries a finite power supply, a finite fuel reserve for adjusting its orientation and trajectory, and a finite tolerance for accumulated radiation damage before its most delicate systems finally give out. Repair, in any traditional sense, is simply not possible across distances measured in hundreds of millions or billions of kilometers. Every fix must be performed remotely through software patches transmitted at the speed of light and executed by processors that may themselves be slowly degrading. There is an inevitable point for every mission where the accumulated wear of the vacuum, the radiation, and the sheer passage of time outpaces our ability to compensate from a control room on Earth. The engineering triumph of these missions has never been that they last forever. It has been that they last so much longer than anyone had any right to expect, squeezing genuinely extraordinary scientific returns out of hardware that was, in some cases, designed with expectations of a mission lasting only a fraction of the time it ultimately achieved. None of this means engineers are standing still, simply hoping newer missions will fare better by luck. Forecasting solar activity has become considerably more sophisticated in recent years, with agencies operating dedicated spacecraft, including instruments positioned at a gravitationally stable point between Earth and the Sun, to provide continuous, uninterrupted monitoring of the solar surface and the incoming solar wind. These observations feed into models, increasingly assisted by machine learning techniques trained on decades of historical flare and coronal mass ejection data, that attempt to provide advance warning of dangerous activity, sometimes with enough lead time for mission controllers to command a distant spacecraft into a protective configuration before the most damaging particles ever arrive. This forecasting is not perfect, and predicting the exact timing, intensity, and direction of a coronal mass ejection remains a genuinely difficult problem in space physics. But the improvement compared to even a couple of decades ago has been substantial, and every mission currently in flight benefits from a warning system considerably more capable than anything available to earlier generations of spacecraft. Future missions are also being designed from the outset with this hard-won knowledge already built in, rather than treating radiation as an afterthought bolted onto an existing design. Proposed and in-development missions intended to explore the icy moons of the outer solar system, to return samples from asteroids passing through more energetic regions of the inner solar system, and to eventually support longer human stays on the lunar surface as part of the broader Artemis program. All incorporate lessons learned directly from the failures, close calls, and slow, patient successes of the missions that came before them. Every safe mode entry, every unexpected instrument anomaly, and every additional year a spacecraft manages to survive its predicted radiation budget becomes another data point folded into the next generation of shielding calculations, rad-hardened chip designs, and mission timelines. In this sense, the fleet of aging Voyagers, the vaulted spacecraft orbiting Jupiter, and the human-rated capsules being designed for a future Mars mission are not separate stories at all. They are chapters in a single, continuing engineering conversation with the same relentless physical environment, each one slightly better informed than the last. All of this brings the conversation back to the question at the very center of the topic: whether humanity is capable of moving beyond being a purely planetary species, tied entirely to the protective conditions of a single world, or whether the physics of radiation, power decay, and the sheer emptiness of space represents a genuine, permanent ceiling on how far we can meaningfully go. It would be inaccurate and unscientific to declare this question already answered in either direction. What can be said, based on current evidence, is that every mission flown so far has demonstrated that the challenges are severe, but not, so far, insurmountable, provided engineers correctly anticipate the environment a spacecraft will face and build in appropriate margins of safety. Solar Cycle 25's unexpectedly vigorous activity throughout 2026 is a reminder that some of those margins were tested more aggressively than models predicted, and mission teams have had to respond in real time, relying on safe mode protocols, redundant systems, and increasingly sophisticated ground-based signal processing to keep their spacecraft alive and their data flowing. Meanwhile, plans for crewed missions to Mars continue to depend on solving the harder, still partially open problem of protecting human biology across a multi-year transit through a radiation environment that no astronaut in history has ever experienced continuously for that length of time. What remains genuinely unknown is not whether the sun can produce a flare powerful enough to threaten a spacecraft, or whether cosmic rays can damage human tissue. Both of those things are well established through decades of observation and physical experimentation, going back to Carrington's own telescope sketches in the 19th century and continuing through every mission flown since. What remains unknown is the precise combination of shielding, redundancy, medical countermeasures, and mission design that will ultimately make a multi-year, uninterrupted deep space journey survivable for a human crew, and how long our oldest and most far-flung robotic explorers will manage to keep speaking to us before the last trickle of power in their aging generators finally runs dry. Researchers across multiple space agencies continue to model solar behavior, refine radiation-hardened electronics, and study the biological effects of long-duration spaceflight, precisely because these are not settled questions, but active, evolving areas of science. What is clear is that space has never been simply empty. It is a dynamic, energetic environment shaped by a sun that periodically reminds us of its power, and by cosmic forces stretching back to the deaths of stars long before our own sun ever formed. Every silent voyager currently drifting through that environment, and every human being who may one day follow, exists in a delicate and carefully engineered negotiation with forces that do not care about mission timelines, budgets, or ambition. Understanding that negotiation, in honest and specific scientific terms, is not a reason for pessimism. It is the foundation on which every future mission and every future voyager will ultimately be built. It is worth sitting with just how much has already been achieved despite this hostile environment. A generation of engineers, most of whom never expected to see their own creations still functioning decades after launch. Built the Voyager probes using 1970s-era technology, and those probes went on to outlive their original mission plans by a factor that would have seemed implausible at the time, delivering humanity's first close look at 4 giant planets and their moons before continuing onward to become the first human-made objects to leave the sun's direct influence entirely. Curiosity and perseverance, built around processors chosen specifically for their proven reliability rather than their raw speed, have spent years each grinding across the Martian surface, surviving dust storms, temperature swings, and the accumulated radiation dose of a journey that once worried some of the very engineers who designed their instruments. None of this happened by accident, and none of it happened because the environment turned out to be gentler than feared. It happened because generations of scientists and engineers took the physics seriously, tested relentlessly, built in redundancy wherever mass budgets allowed, and accepted that some risk, carefully measured and continuously monitored, was the unavoidable cost of reaching beyond the safety of home. The unresolved questions that remain are not signs of failure. They are simply the next items on a very long, very old list that space exploration has always maintained, updated with each new mission and each new solar cycle. Will radiation-hardened electronics keep pace with the increasing ambition of missions being planned for the coming decades, as scientists push to send spacecraft closer to more extreme environments, deeper into the punishing radiation belts of the outer planets, or across ever greater distances where autonomous decision-making becomes more necessary precisely because human oversight becomes less immediate? Will medical research resolve with genuine confidence rather than cautious estimation whether the human nervous system can tolerate years of continuous exposure to galactic cosmic rays well enough to make a Mars mission not just survivable, but genuinely safe? And will the aging fleet of robotic explorers currently operating far from Earth manage to squeeze out a few more years of discovery before the quiet mathematics of radioactive decay finally closes the channel between them and the planet that built them? None of these questions have final answers yet. What can be said with confidence is that each one is being actively studied by real researchers using real data gathered from real missions, rather than left to speculation. And each incremental answer, however small, adds another piece to a puzzle that has been slowly assembling itself since the very first spacecraft left the protective boundary of Earth's own magnetic field that, in the end, may be the most accurate way to describe where things currently stand. The sun will keep cycling through its 11-year rhythm, occasionally producing storms more violent than any forecast anticipated, exactly as it has done since long before humans existed to measure it. Spacecraft will keep pushing outward, carrying instruments built with the best radiation tolerance current engineering can provide, and inevitably, some of them will eventually fall silent, not from any single dramatic failure, but from the patient accumulation of decades spent in an unforgiving environment. And somewhere in a mission control room, engineers will keep watching solar forecasts, adjusting spacecraft schedules, and slowly, carefully, expanding the boundary of what human technology, and perhaps one day human biology, can genuinely survive. That expanding boundary, inch by inch, mission by mission, decade by decade, is really the entire story of deep space exploration itself. A story with no true final chapter. Only the next spacecraft, the next solar cycle, and the next question still waiting to be answered.